Welcome to example number 8, which involves masses of astronomical bodies. So up to this point, we've been studying artificial Earth satellites that are going around in circular orbits. But we can apply the same principles to any object that is acted on by gravity in a circular orbit around some stationary object. So some other familiar examples would be the moon, for example, the moon around planets or around Earth. We also have planets that are orbiting around the sun in circular paths. The rings of Saturn, Jupiter, Neptune are all composed of small pieces of matter that are traveling in circular orbits around the planets. So in this kind of example, what we are going to be doing is applying we can use Newton's second law and then come up with Kepler's third planetary law. So let's start off from first principles and use sum of F equals ma, and we have mv squared over r, gmm all over r squared, and we have the following expression: g, mass of the body, the stationary body, divided by r equals 2 pi r all over period squared. So then in the end what we'll get is the following expression. We'll have 4 pi squared r squared t squared gm all over r, and then if we were to rearrange for t squared, we would get 4 pi squared r cubed all over g and m. So we're going to be using this this Kepler's third law to solve this problem. We are given in this particular problem a star, so like the sun, HD 68988. In its orbital distance, there's a planet that is orbiting this star, and it is to be measured as 10.5 million kilometers. So we'll call that R1 is 10.5 times 10 to the power 6 kilometers from the center of the star to the planet. And the orbital period for that is 6.3 days. Then we want to know what is the mass of the star. So we know r and we know t, and we're solving for m. So if we were to rearrange this equation, we would get 4 pi squared r cubed all over t squared. And now we're going to substitute in. We have 4 pi squared times 10.5 times 10 to the power of 9 meters, because this is really kilometers and we need to change this to meters, cubed all over the period, which is going to need to be written in seconds. So 6.3 days, we need to multiply this by 24 hours over 1 day, then 60 minutes all over 1 hour, and 60 seconds in 1 minute. And you should get approximately 5.443 times 10 to the power of 5 seconds, and this is squared, this quantity. And I just realized that I'm missing as well g down here, so this is also multiplied by 6.67 times 10 to the power negative 11 in units of Newton meter squared per kilogram squared. And when you plug that all into your calculator, you should get approximately 2.3 times 10 to the power of 30 kilograms. So this is the mass of the star. Now they also wanted to compare this to mass of our own sun. And the mass of our sun is 1.2 or actually 1.99 times 10 to the power of 30 kilograms. So you could Google that and see that it's that value. And so if we want to find what this was in terms of that, you would take 2.3 times 10 to the power of 30 kilograms and divide it by 1.99 times 10 to the power of 30 kilograms for our mass of the sun, and you'll find that the mass of this star is about 1.2 of our mass of our sun. So in summary, this example shows that if you know just two pieces of information, the radius of orbit and the period around this stationary object, then you can find approximately what the mass of that stationary object is. So we can use this to apply this to satellites, their moons that are around Jupiter, and determine the mass of, for example, Jupiter. And that's how we find out masses of different planets in our solar system. And that's it for this example.